It is the most familiar force in our lives, yet it remains one of the most profound mysteries in all of science. It is the invisible thread that keeps your feet planted on the ground, the tether that keeps the moon in orbit around the Earth, and the master architect that sculpts the very fabric of the universe. Without it, there would be no stars, no planets, no atmosphere to breathe, and no complex life to wonder why. It is a force that is simultaneously incredibly weak and infinitely powerful. Today, we dive deep into the invisible grip of the cosmos. This is the story of gravity, the force that shapes the cosmos. To understand gravity, we must first realize how strange it is compared to the other forces of nature. If you pick up a small refrigerator magnet, it can overcome the gravitational pull of the entire Earth to lift a paperclip. On a subatomic level, gravity is so weak it is almost non-existent. And yet, over vast distances, it is the undisputed king. It is the only force that acts across the entire span of the universe, pulling on every atom, every star, and every galaxy, regardless of how far apart they are. It is the ultimate connector. For centuries, our understanding of gravity was defined by Sir Isaac Newton. Legend tells of an apple falling in his orchard, sparking a realization that changed the world. The same force that pulled the apple to the ground was the force that kept the moon from flying off into space. Newton described gravity as an invisible pull between objects. The more mass an object has, the stronger its pull. The closer you are to it, the more powerful that pull becomes. It was a beautiful mechanical view of the universe that allowed us to predict the movements of planets with incredible precision. But Newton himself admitted he didn't know how it worked. He could calculate the force, but he couldn't explain what it actually was. That explanation wouldn't arrive for another 250 years, brought to us by a patent clerk named Albert Einstein. In 1915, Einstein presented his general theory of relativity, and it shattered our common-sense view of reality. Einstein realized that space and time are not separate, static stages. Instead, they are woven together into a four-dimensional fabric called space-time. He proposed that gravity is not a pull in the traditional sense, but rather a curvature of this fabric. Imagine a stretched-out trampoline. If you place a heavy bowling ball in the center, it creates a dip or a curve in the fabric. If you then roll a marble across the trampoline, it won't move in a straight line. It will roll toward the bowling ball, following the curve of the fabric. In this analogy, the bowling ball is a star or a planet, and the marble is an object moving through space. Gravity isn't an invisible string. It is the shape of space itself. As Einstein famously put it, matter tells space how to curve, and space tells matter how to move. This revolutionary idea led to some mind-bending predictions. If gravity is the curvature of space-time, then it shouldn't just affect objects with mass, it should affect everything, including light. Einstein predicted that a massive object, like the sun, would bend the light from distant stars passing near it. In 1919, during a solar eclipse, astronomers proved he was right. They saw stars appearing in slightly different positions because their light had been bent by the sun's gravity. This gravitational lensing is now one of our most powerful tools for studying the distant universe. We use the gravity of entire clusters of galaxies as a cosmic magnifying glass to see the first galaxies that ever formed. But gravity's influence goes even deeper. Because space and time are linked, gravity doesn't just bend space, it bends time. This is known as time dilation. The stronger the gravity, the slower time passes. This isn't just a theoretical concept. It is a practical reality. The clocks on GPS satellites which are further away from Earth's mass and therefore in a weaker gravitational field, actually tick slightly faster than clocks on the ground. Engineers have to account for Einstein's equations of gravity every single day, or your phone's GPS would be off by miles within 24 hours. If you were to stand near the edge of a black hole, where gravity is extreme, an hour for you might be decades or even centuries for someone back on Earth. Gravity is the ultimate time machine. In the grand history of the cosmos, gravity is the force of creation. In the early universe, just after the Big Bang, the cosmos was a nearly uniform soup of hydrogen and helium. But there were tiny, microscopic fluctuations in density. Gravity took these tiny seeds and began to work its magic. It pulled gas together into the first clouds, then compressed those clouds until the first stars ignited. It gathered those stars into galaxies, and those galaxies into the vast cosmic web we see today. Gravity is the reason the universe isn't just a boring, expanding cloud of cold gas. It is the reason there is stuff instead of nothing. Gravity also governs the life and death of every star. As we've explored in previous episodes, a star is a delicate balance between the outward pressure of nuclear fusion and the inward crush of gravity. For millions or billions of years they sit in equilibrium. But gravity is patient. It never gets tired. It never runs out of fuel. The moment a star runs out of energy to push back, gravity wins. It crushes the star's core into a white dwarf, a neutron star, or in the most extreme cases, a black hole. A black hole is the ultimate triumph of gravity. It is a region where the curvature of space-time is so extreme, the dip in the trampoline so deep that nothing, not even light, can ever climb back out. It is a place where gravity has essentially broken the universe. At the center of a black hole lies a singularity, a point of infinite density where our current laws of physics simply stop making sense. Gravity takes us to the edge of the known and leaves us staring into the abyss of the unknown. But gravity's story isn't just about the massive and the spectacular. It is also about the subtle and the invisible. We've discovered that there is far more gravity in the universe than we can account for by looking at stars and gas. Galaxies are spinning much faster than they should be. They should be flying apart like mud off a spinning tire. This led to the realization that there is a missing source of gravity, dark matter. This invisible substance doesn't emit light or interact with anything except through gravity. It provides the extra grip needed to hold galaxies together. In fact, there is 5 times more dark matter in the universe than normal matter. Gravity is our only way of knowing it's there. On the largest possible scales, we are currently witnessing a cosmic tug-of-war. Gravity is trying to pull the entire universe back together, but a mysterious force called dark energy is pushing it apart, causing the expansion of the universe to accelerate. For the first 9 billion years of cosmic history, gravity was winning, allowing structure to form. But about 5 billion years ago, dark energy took the lead. The fate of the universe, whether it will eventually collapse back in a big crunch or expand forever until it becomes a cold, dark void, depends entirely on the balance between gravity and this dark energy. One of the most exciting recent breakthroughs in our study of gravity was the detection of gravitational waves. Einstein predicted these in 1916, but they weren't detected until 2015, when 2 massive objects, like black holes or neutron stars, collide. They send ripples through the fabric of space-time itself, like ripples in a pond. These ripples travel across the universe at the speed of light. Detecting them was like humanity suddenly gaining a new sense. For thousands of years, we could only see the universe through light. Now we can hear the universe through gravity. We can listen to the symphony of colliding black holes and the silent vibrations of the cosmos. Gravity also plays a vital role in the habitability of planets. The gravity of a planet determines how thick its atmosphere is. If Earth's gravity were much weaker, our atmosphere would have bled away into space long ago, leaving us a dead rock like Mars. If it were much stronger, we might be crushed under the weight of a massive, crushing air column. Gravity even helps regulate our climate by keeping the Earth at a stable distance from the Sun. It is the golden thread that makes life possible. Yet, for all its power, gravity remains the black sheep of physics. We have been able to unify the other three forces of nature, electromagnetism, and the strong and weak nuclear forces, into a single mathematical framework, called the Standard Model, but gravity refuses to fit. It operates on the scale of the massive, while the other forces operate on the scale of the tiny. Finding a theory of everything that can unite gravity with quantum mechanics is the holy grail of modern science. It would be the final piece of the puzzle, explaining how the universe works from the smallest subatomic particle to the largest supercluster. As we look at the world around us, it's easy to take gravity for granted. We complain when we drop a glass or when we have to climb a flight of stairs. But that same force is what gives the universe its shape. It is what allows the sun to shine and the earth to turn. It is the most democratic force in existence. It treats everyone and everything the same, from a grain of sand to a giant star. Gravity is a reminder of our connection to the rest of the cosmos. Every atom in your body is pulling on every star in the Andromeda galaxy, and those stars are pulling back on you. You are part of the cosmic web, held in place by the same force that guided the first light after the Big Bang. We are not just standing on a planet. We are participants in a 13.8 billion-year-old dance of mass and energy. The study of gravity is the study of the limits of our knowledge. It takes us from the falling apple to the warped light of distant galaxies, and eventually to the dark heart of the black hole. It challenges our understanding of time, space, and reality itself. And the more we learn, the more we realize how much more there is to discover. Thank you for joining us on this weightless journey through the most fundamental force of all. Gravity might be invisible, but its effects are written across the entire sky for those who know how to look. If you enjoyed this exploration into the force that shapes our world, be sure to subscribe and hit the notification bell for our next episode. We'll be diving into even deeper mysteries of the universe, from the beginning of time to the edge of the void. Until next time, stay grounded, keep looking up, and never stop wondering about the invisible forces that move the stars. Safe travels through the wonders of space-time.